So in this video, we'll continue our discussion on different filter types. So we are going to discuss about all pass filters. So what are all pass filters? So they have got same magnitude response for all omega, which means they pass all the frequencies in the same way. In the same means in the magnitude, there is no change in the magnitude, but only change in the phase. The phase delay is different for different frequencies, but all frequencies are passed without attenuating them or enhancing them. Or attenuating or enhancing in the same way. Basically, it can multiply with a constant factor, but it won't differentiate between them in terms of magnitude gain. Okay, so the basic definition of an all-pass filter is that the magnitude response is constant with respect to omega, right? This is constant with respect to omega. So it does not depend on omega. All the frequencies are equally enhanced or attenuated. Uh, and ideally we'll put k equal to 1, right? So that it does not affect them at all. But the frequency response, the phase response will be not zero, which means it will introduce different delays, because somebody may think, okay, e to the power j omega is simply a constant k, or under root of k, okay, whatever. But if this is simply constant, then that also is an all pass filter, but then it does not do anything to the frequencies, and so this filter is just a gain. So that is not the purpose. The purpose is to have different phase changes to different frequencies. Okay, so with that basic definition, let's formulate a canonical form of all pass filters. The canonical form is something like this. So basically, DMZ is a polynomial in Z of degree capital M. So M is the number of roots of DMZ, right? And DMZ inverse is the same DMZ, but it's a polynomial of Z inverse. The same polynomial, the variable is Z inverse instead of Z. Okay, and you multiply it with Z to the power minus M. The reason for this is that you want to have all the terms in the negative powers of Z. Okay, so let's move on. Let's study this canonical form in bit more detail. Okay, so generally we take a positive sign here. Okay, means what is negative sign? Negative sign, magnitude. Okay, so what does negative sign do? So for the magnitude response, uh, does not affect, does not, okay, is not affected. Okay, so magnitude response is not affected by negative sign. The phase response, angle AM e to the power j omega, this is affected. How? That the negative sign will just introduce a pi phase, right? Is so you so this basically so this adds pi. So negative sign adds a pi to my phase response. So I can ignore the negative sign for the time being and just focus on the positive part of it. Okay, so now DMZ, let us say my DMZ has a 0 at or a root at A. Then DMZ inverse will have a root at 1 upon A, right? We have studied this in our previous discussions. Let us say this is my Z plane and this is my unit circle. If I have a root at A, this means I have a pole for AMZ at A. Let's say this is my A. And DMZ inverse will have a root at 1 upon A, which means AMZ will have a 0 at 1 upon A. So this is 1 upon A. So this is how AMZ will look like, right? I have a pole at A and a 0 at 1 upon A. Okay. Now, for stability, you know that the poles should be inside the unit circle. Okay, let's take an example when dz is a 1 order degree 1 polynomial d1z. So basically my m is equal to 1. Now what is amz here? So my a1z will be equal to z to the power minus m dm z inverse, so basically d1, so 1 plus 0.5 z inverse, so this becomes z divided by d1z, so which is 1 plus 0.5 z inverse. Right. Okay, let's study what is the magnitude of a response. So basically a e to the power j omega, this is equal to e to the power minus j omega, and let me take 0.5 common, it becomes e to the power j omega plus 2, right? If I take 0.5 common, it becomes 2 here, divided by e to the power minus j omega plus 2, right? So let me draw it here. So on the unit circle, so basically I have got pole at minus, sorry, I won't discuss in terms of poles or zeros. I will just say, let us think this point. So basically my magnitude of a e to the power j omega. This is simply, the first term is 1 because e to the power minus j omega, the magnitude will be, this is e to the power j omega plus 2 divided by e to the power minus j omega plus 2. So this term is the distance of the point e to the power j omega. So this angle is omega, and distance from the point minus 2, where we have minus 2. So this length, let me draw it with yellow. So this is the distance, right? And I may have, and another point is e to the power minus j omega, so which is exactly the mirror image here, e to the power minus j omega, where this is omega, right? And the denominator term is the distance of e to the minus j omega from minus 2. So this is the term. So, and you see both of them are by symmetry equal. So my a e to the power j omega magnitude becomes equal to 1, right? Now let's consider the phase term, the phase of a e to the power j omega. This will be equal to, okay, minus omega, right, plus angle of e to the power j omega plus 2 minus the angle of e to the power minus j omega plus 2. Okay, so what is this angle? So let me use yellow color. So this angle is e to the power j omega angle. So this is the angle, right? So this is the angle. And the second term is, so this is the angle. So let's say if this is theta, this is minus theta, right? So this is the angle. And you see both are same in magnitude, but signs are different. This is plus theta, this is minus theta, and minus minus get cancelled. So what we get here is, this is equal to minus omega plus, if I call it as theta, so let me say this is theta, then the blue one will be, this is minus theta, right? So this becomes plus theta minus minus theta, so which means twice of theta. So minus omega plus 2 theta. So this is my angle. So let us see how the angle will change. So in the beginning, the angle will be increasing, the theta will be increasing, and theta will go to 0. So let me say if I have to plot the phase response, okay, if I have to draw a phase response between 0 to pi, then what I find is the theta, it increases and then decreases. So the 2 theta term, it increases and decreases. So this is for theta. And the omega term, it always decreases and it becomes, it is just linear, right? I'm sorry, my drawing is not, it doesn't look like a line here, but yes, it is a straight line. So this is minus omega term. So how does the final plot look like? The final plot will look something like this, maybe. Right, the final plot. So, but essentially what we see is it decreases from 0 to minus pi. Okay, so that is the idea, that my phase plot, my phase is decreasing. Okay, so phase is decreasing, and for a general AMZ, the angle will be, angle at 0 is 0, right? At 0, when omega is 0, then the angle is 0, as you can check here, you can see here, dm when z is e to the power 0, basically 1. So dm1 and dm1 here, both are 0 angles. 0 to the power minus m, that is also 1, so 0 angle. So, and it goes from 0 to minus m pi. So at 0 it is 0, and then it, whatever it does in between, it finally goes to, at pi it goes to minus m pi, right? So that is the idea. The phase of AMZ is decreasing. Okay, so this was about all pass filters. In the next video we'll be discussing about min and max phase filters. Thank you very much.